So here's a simple question. We have a helium balloon, and what makes it float? Odds are you're thinking, well, that's easy. It's the force of buoyancy. And if the force of buoyancy is bigger than the weight of the balloon will accelerate upward. But if the buoyancy force is less than the weight of the balloon, then the balloon will accelerate downward. And if the buoyancy force is equivalent to the weight of the balloon, then we say the balloon is neutrally buoyant and it neither goes up or down. My question for you is, what causes the force of buoyancy? We know that weight is caused by Earth's attraction to objects, gravity acting downward, but there's no celestial body, for example, out in space that decides that lighter things ought to be pulled upward. Intuitively, we know that light things float, but why is that? Some of the common misconceptions I've heard is that maybe there's a lower pressure of the gas inside of the balloon, and that causes it to go up. But in the case of a helium balloon, I'd argue the pressure inside the balloon is actually greater than the pressure outside of the balloon because of the contractive forces of the rubber. Another misconception is that the gas inside of the balloon weighs less than the gas outside. But I would argue that even though that might be true, the gas inside still has a weight, and gravity still pulls down on that gas no matter how heavy it might be. So the weight of the gas itself doesn't explain why the balloon floats upward. The answer to this question is it's actually the air outside of the balloon pushing upward on it, which holds it off the ground. And we see that atmospheric pressure, the pressure forces always act normal to the outer surface of the balloon, but the pressure at the bottom and the top of the balloon are different, and there's actually a higher pressure at the base of the balloon than there is at the top. The reason the pressure at the top of the balloon is less than the pressure at the bottom of the balloon is simply because it's higher up in the atmosphere. And this is fascinating to me because I tend to think of changes in barometric pressure associated with thousands of feet or thousands of meters, perhaps, of elevation gain. For example, the pressure in the mountains is a great deal less than the pressure at sea level. But here we have a helium balloon that's on the order of a foot or even less, several centimeters high even, a small balloon would float. And when you feel the balloon pulling upward, what you're really feeling is that very small change in atmospheric pressure between the top and the bottom of the balloon. As I'm sitting here, I certainly don't think about the fact that the air pressure at my feet is greater than the air pressure at my head, but it's very much the case, and you can realize that even with an object as small as a helium balloon. To demonstrate how to come up with an equation for the force of buoyancy, let's consider a rectangular block that's submerged in water. At the surface of the water, the pressure is atmospheric pressure. It's a free surface, and at the top of the block submerged some distance h0 from the water. The height of the block we'll call h, the depth of the block into the screen is d, and the width of the block is w. A force balance of all the external pressures on the box we could say is the force of buoyancy, and that's equal to the force of pressure at the bottom minus the force of the pressure at the top of the box. There are also pressure forces acting to the left and to the right of the box and also into and out of the screen, but they're equal and opposite and they'll cancel each other out. I can write the pressure force at the bottom as equal to PB, the pressure at the bottom of the box, times the area at the bottom of the box, minus the pressure at the top of the box times the area at the top of the box. The pressure acting upward at the bottom of the box is simply the fluid static pressure, which is atmospheric pressure plus rho g, the density of water times gravity, plus the distance between the water surface and the bottom of the box, which is h0 plus h. The area of the bottom of the box is simply the width times the depth of the box into the screen. And the product of these two is simply the force acting upward at the bottom of the box. The force of pressure acting downward on the top of the box, again, is fluid static pressure, which is atmospheric pressure times the density times gravity times the submerged height at the top of the box, multiplied by its area, which is again W times D. And if I subtract these terms, what I find is that atmospheric pressure cancels out. This term regarding in relation to H0 cancels out. And what I'm left with is the density of water times G times HWD. H times W times D is simply the volume of the box, so I can write this as rho GV. And this is better known as Archimedes' principle, in which the force of buoyancy is equal to the weight of the water displaced by the object. If I wrote that mathematically, the density of the water displaced multiplied by the volume of the object is simply equal to the mass of the water displaced times gravity, which is the force of buoyancy. Note that because atmospheric pressure and h naught canceled out of my formulation, the force of buoyancy has nothing whatsoever to do with atmospheric pressure, nor does it have anything to do with the submerged depth of the object. Moreover, it also doesn't have anything to do with what's inside of the box, or inside of the object that we're considering. It only has to do with the density of the surrounding fluid. Here's a related question. What makes a hot air balloon float? You're probably thinking the density of the hot air inside of the balloon is less than the density of the surrounding air, which is true because it's hotter. But the conundrum that I had is that the hot air balloon is open at the bottom. And what that means is that the pressure at the bottom of the balloon, the pressure of the hot air, has to be equal to the pressure of the surrounding atmosphere. What that means is if I drew a vector representing a pressure inside the balloon, it's equal and opposite to atmospheric pressure at the bottom of the balloon, and the pressures exactly cancel each other out. So the question remains, why do hot air balloons float? To try to get at this question, challenge yourself with this. Draw for me the pressure as a function of z, where z is the height above the opening at the base of the balloon. And on this graph, I want you to draw two curves, the pressure at the inside of the balloon and the pressure outside of the balloon. Let's do the outside of the balloon first, so the pressure of the atmosphere. And we'll start at z equals 0, where P is equal to atmospheric pressure. And as z increases, the pressure reduces about linearly. And what this says, just like the closed helium balloon, the pressure at the base of the balloon, these vectors are larger at the bottom than they are at the top. Additionally, the slope of this line is equal to negative rho times g, where rho in this case is the density of the surrounding atmosphere. Think about what would happen if the density of the air is reduced. What that means is that the slope is less and less negative. At the base of the balloon, z equals 0, the pressures have to be equivalent because the balloon is open, but the density of the air inside the balloon is less than the density outside of the balloon, and what we see for the inside of the balloon is that as you move upward from the opening, the pressure does decrease, but it doesn't decrease as much as the atmospheric pressure surrounding the balloon. And indeed, at the top of the balloon, the pressure inside the balloon is greater than the pressure outside, and that's what supports the balloon. You can double check my calculations if you like, but for a typical balloon that might be 80 feet tall or 24 meters tall, and at an average temperature of 100 degrees centigrade inside of the balloon, what we'll find at the top of the balloon, the pressure differential between the inside and the outside of the balloon is about 60 Pascal. And 60 Pascal is only about equal to 1/100th of a psi. However, it's the fact that hot air balloons are so very large, maybe 15 or 16 feet in diameter, that they can support over 1,000 pounds with such a small pressure differential.